Hello again, this is Professor Jim Caffey, based in Springfield, Missouri, along with my two dogs, Orion and Mr. Man, you've met earlier. And today we are going to do out of the OpenStax Astronomy free textbook, Chapter 22, Stars from Adolescence to Old Age. This is called the Ant Nebula. It is a remnant of a star that has exploded. Very beautiful. We're getting into deep with how stars work and the physics behind it. Here we have layers inside a star before and after it leaves the main sequence. And what does it do? Here are some relative sizes of stars. You can see the Sun over here to the left, and Delta Bootes and Xi Cygni is up here. Very big stars. Betelgeuse is a red supergiant. You can see it outside in the wintertime, late fall, winter, early spring. Rigel is in the top left-hand corner of the shoulder, and a very cool but big star, low in temperature. We talked a little bit in chapter 21 about stars leaving the main sequence, how they evolve. So depending on how many solar masses, how many times the Sun in mass it is, it will determine when and how it turns off the zero-age main sequence and evolves into an older star that's not doing fusion like the Sun. This is Omega Centauri, and you might see this in Arizona. I cannot see it in Missouri, but when I was in Tucson 20 years ago, I was able to stand on top of the mountain and see this huge globular star cluster way low in the distance on the horizon. So if you go outside, you may see this. It is a southern hemisphere object, 16,000 light years away. Here is the jewel box, and we give some of these extragalactic items names called NGC, New Galactic Catalog, and a number. Astronomers love catalogs. We have dozens of catalogs with weird names. So we can also look at clusters of stars. We can determine and assume that all the stars in a star cluster are going to be about the same age. So that whole cluster should turn off at about the same time. And we can determine the age of that cluster based on how and when it does get off the main sequence. And that's really neat. Another young cluster, NGC 2264, 2600 light years away. This is called the Christmas tree cluster. Very pretty. Here is another cluster on an HR diagram. We can theoretically determine what this graph will look like, but we have to get to a telescope and we have to look at these stars and determine all the properties of them with a telescope. Here's another nebula star cluster. We can see the light in the cluster being red, lit up by these hot blue stars. Older clusters are going to turn off higher up, so they will follow the main sequence line and then turn off and go up. This is a really famous cluster, 47 Tucani. And you can see here how it lines up. A very good pattern. More clusters of different ages. A new cluster is a zero-age main sequence. We can turn off early at 100 million years, and we can turn off late in 10 billion years like the Sun will. So here is the evolution of a star like the Sun on an HR diagram. We go on the main sequence to start. Once a star like the Sun begins to die, it will leave the main sequence and it'll make a track up here to a helium flash. All the hydrogen is going to run out, and they're going to take the helium that's in the core and start burning it like burning ash. So it's a very quick, hot process. It comes back towards the main sequence, but it doesn't all the way get there. And then we go into more helium flashes now in the shell, the outer part of the star. And so a low mass star, we can think of that as the Sun, has these shells in it: a hydrogen envelope, hydrogen shell fusion, helium core, helium fusion, and even beyond that, a carbon-oxygen core. More beautiful planetary nebula. Why are they called planetary nebula? They have nothing to do with planets. Well, in a telescope, they look a little three-dimensional. They do look three-dimensional. And that's how planets look too, so it gives them that name. But these are the remnants of stars that have died, and we see such beautiful art and space in the universe. Here is the most famous one. This is Eta Carinae. This is in the southern hemisphere. We cannot see this from the United States. It is way far south by the pole. We have a very massive star working on exploding and dying. And so we are seeing this in a very rare case that we don't usually see. We either see it before or after it has evolved. And this one is doing it now. This is the shells for a massive star. So we have the same shells, but we get more shells going in this. Magnesium, oxygen fusion, silicon and sulfur fusion. Can you imagine? And then in the bottom is iron ash. We cannot fuse iron in a star. And so that is the point when it explodes into a supernova. Thank you again for joining us and the dogs for chapter 22.